Welcome, this is Dr. Ali Mogable. In this video, we'll cover some modulation techniques. The techniques we are going to cover are typically the new ones. We have another video about ASK, PSK, FSK. I can share the link to the basic digital modulation techniques. But here we'll focus on FSK, MSK, and noncoherent orthogonal modulation. We'll look at also at DPSK. The material here is found on most of the popular textbooks, including Haken, for example, and Goldsmith. If you want the slides or additional resources, you may visit my website or search for Mogable, and you can find additional material. The outline of this video will start with linear and we'll start with classifying modulation techniques into linear and nonlinear. Then we'll pick some of these, including the frequency shift keying. We'll look at an error probability of FSK, MFSK, and spectral efficiency. Then we'll move into MSK, minimum shift keying, noncoherent orthogonal modulation. That will include noncoherent binary FSK and DPSK. In coming videos, we'll look at a comparison between digital modulation techniques in terms of performance. So let's start by classifying linear and non-linear modulation techniques. So modulation techniques can be classified as linear, that includes ASK, MPSK, and QAM, amplitude, phase, and QM. So we can think of this circle. I'm just showing here, for example, PSK and QBSK, or offset QBSK. On the left-hand side, we have the non-linear modulation techniques, which includes FSK and MSK, minimum shift keying. So since we have covered these in previous videos, we'll focus on the nonlinear modulation techniques. That's an example of PSK. Since all the constellation points are in a circle, they have the same amplitude, same distance from the center, but they have different phase. So amplitude shift keying will have only one base function. We have seen this before. I'll share the video with you. But for now, we'll focus on the more advanced ones that we haven't seen before in details. Let's start by the binary frequency shift keying. In binary frequency shift keying, the transmitted signal is either 0 and 1, and this is because we are dealing with binary. And since we are dealing with frequency shift keying, what we are going to transmit is a signal which has different frequencies. So in case of 0 or 1, we have two signals, S1 and S2. So I changes from 1 and 2. And we have square root of 2 over TB just to normalize the original signal. And that would be scaled by square root of AB, where AB is the energy of the signal, energy per bit in our case, because we are dealing with binary. So basically in frequency shift keying, we distinguish the two symbols by the frequency Fi. To make sure that the frequencies are properly chosen, so Fi equals to Ni plus I, where I is just 0 or 1, divide by TB. So it's a scaled version of 1 over TB, where Nc is a fixed integer. The symbol 1 is represented by S1, and the symbol 0 is represented by S2. So I is either 1 or 2. Now we have two waveforms, S1 and S2, which are orthogonal. If these are the signals, sorry, if you want to normalize, this EB will disappear. So these are the bases. They're just exactly the same, just for completeness. EB should equal to 1 for the normalized bases. We usually choose the binary phase frequency shift keying to make sure that the phase is continuous. Because when we change the frequency, we want to make sure that we are changing it gradually to avoid phase discontinuity, as we're going to see in the coming slides. Now, when it comes to the constellation diagrams, we have the binary phase frequency shift keying. We have, just like we mentioned, we have two bases, and those two bases are the sinusoids with two frequencies. This is the first base, and this is the second base. You can see the difference in the frequency. And we can think of this if you're sending one of these bases, so with the proper energy, so we can represent the signal 1 with vector square root of EB and 0. Similarly, we'll have 0 and square root of EB for the second signal. So you notice here what's important to find the probability of error is the distance between the two. This is not like binary phase shift keying where we have two in the same axis. Now the distance here using geometry will be just square root of 2 EB. So the coefficient for the two signals are 1 and 2. We just mentioned that if you want to get if you want to get the vectors, you project the signal on the basis, and of course you get what we had before. So you do the projection, and we get, of course, square root of EB. We can do it in details, but that's obvious because we already selected the basis function to make sure that they are normalized energy. So they look similar. You can do that for the second signal also. So these are the bases, and we see that what's important here is in the constellation diagram and how far these two together, because that will determine the performance of binary frequency shift keying. We'll assume that we are dealing with coherent, so the receiver knows exactly the phase and can compare with the basis function. Now if you look at the error probability and we try to compare the binary case with the frequency shift keying case, we have here a reduction in power. Here we have, if you compare the distance here with the distance here, you'll find that this is much greater, and then there's a factor of 2. So this is the probability of error for the case of frequency shift keying. And if you compare the case for binary phase shift keying, then binary would have less. I mean, it has a less error, which is better performance, because the error complementary function will have the amount of energy per noise here would be stronger. So clearly binary phase shift keying outperforms frequency shift keying. And of course there's a factor of double here. In signal space diagram, the Euclidean distance is the minimum distance here is 2 times square root of EB. However, in the case of binary frequency shift keying, it's the square root goes inside. So there is a clear advantage for phase over frequency, but this does not mean that there are no application or there are no scenarios where frequency would be more appropriate. Now let's get some comments about minimum shift keying. If you recall, for the case of coherent phase shift keying or binary phase shift keying, we're just focusing on the frequency. So the difference between 0 and 1 is in the frequency. The phase of the signal was never exploited. Only we just use coherent for synchronization, but we did not distinguish 0 and 1 using the phase. Now in minimum shift keying MSK, we can improve the performance by exploiting the phase of the signal. The minimum shift keying MSK scheme is important because it's used in GSM, in global system for mobile communication. So that's some real application. A pioneer and a widely used digital cellular mobile system, which is the GSM. MSK can be viewed as either a special case of binary continuous phase frequency shift keying, which we are doing now because we just finished frequency shift keying, or we can think of MSK as a special case of offset QPSK, offset quadrature phase shift keying. This is just to keep you in your mind. For now, just keep this on the side and think about the continuous phase frequency shift keying, which we just came from. We are exploiting the phase. So consider these two signals. Okay, we didn't have this red part. We just have two signals with different frequency. Now we'll try to exploit the phase. So there will be some condition in the phase. So the phase at 0 denotes the phase value at 0, which includes everything, which sums up everything in the past. Okay, so everything remains the same. EB is the energy and TP is the duration of the bit. The selection of the frequency will be determined by, are we transmitting 1 or are we transmitting 0? So for the case of selecting the phase for the minimum shift keying, we just have this expression before. In general, the frequency is either F1 or F2, and the phase itself will be selected according to a formula. So the starting phase plus or minus pi times d divided by TB times t. So we're putting some condition, some steps in changing the phase to keep the phase continuity, to avoid having large jump on the phase. Now, the deviation, the scaling factor of the phase, of course, it depends on the difference between the two frequencies, and divide by the frequency of the bit duration, which is 1 over TB. Let's divide by, these are the frequencies. If you divide by 1 over TB, okay, then of course the TB goes up and we get back to where we are. So it's TB times F1 minus F2. So it relates to the frequency of the two carriers, for 1 and for 0. Now if the bit that we transmit, if the symbol is 1, then the phase will include the positive sign, we'll add the positive quantity here. If the symbol is 0, we'll have the negative quantity, so the phase will be subtracted. So if you can see a tree, if this is a time, okay, we'll be moving steps at a time, so going up or down. This is the phase, by the way. We're just gonna go into steps. Okay, let's focus on the phase equation. The phase equal to theta 0 plus or minus this quantity. Now let's just focus at the end of the time duration of the bit at t equal to TB. So this part in green will cancel out because t equal to capital TB equal to TB, so will cancel out. What remains is plus or minus pi d. So the difference between the phase at the beginning and at the end of the bit duration would be plus pi d or minus pi d, depending on the 0 or 1. Sending a symbol 0, sending the symbol 0 increases the phase by pi d. However, sending the symbol 0 reduces the phase by pi d. Alright, so different variations of phase, different data sequence will result in different tree, different phase tree or phase trellis, which is what we are showing here. Here's the time axis, and here is the phase difference between TB and 0. So if you get symbol 1, you just keep adding pi d, so you move up. If you get 0, you move down, up, down, depending on the data. So you create a tree. For the special case where we have d equal to 1/2, this is called minimum shift keying. D is the minimum for the case of minimum required spacing between the frequencies. We get d equal to 1/2, and then we get the phase difference would be plus or minus pi over 2. So this is as a special case. Now let's look at the example of minimum shift keying. And this example determines the phase trellis for a binary sequence 1101-000 with the initial phase of 0 and d equal to 1/2. D equal to 1/2, he guaranteed that we have a minimum shift keying. Remember that the difference d is related to the frequency and the bit duration by the following equation. If we make d equal to 1/2, then we get f1 minus f2 equal to 1 over 2 TB, which is the minimum frequency deviation, which is the minimum frequency spacing between f1 and 2 to be coherently orthogonal. So we cannot make it less than this, and this is why we call it minimum shift keying. That's the minimum shift in the frequency that keeps orthogonality. So if you want to determine the trellis, remember that here the theta would be plus or minus pi over 2. That's if you substitute 1/2 at TB, this is cancels out, and you get the phase relative to the phase 0 would be going up from 0 to pi over 2 because we have 1, another pi over 2, 1, and then we have for this 0 you go down, 1 you go up, 0, 0, 0 you go down. That's it. I'm just showing here another example which has nothing to do with this data stream, but to show that the waveform will have low frequency for 1, high frequency for 0, so that's the frequency part, and the phase would be chosen properly so that we have continuous phase. Okay. To get an idea about the signal space of MSK, for MSK we can think of having two dimensions, although we are not showing the details here, but we can think of having two dimensions, and there are four possible messages M. That's because it has a memory. So there are, although we're having binary, but we have four possibilities. So we have four different possibilities. So one would ask, what is the difference between QPSK? Because in QPSK we're having four possibilities, four different phases, and it's the same for MSK. The difference is in QPSK the symbol can be any of the four messages. So at any given time we can send 1 out of 4, which means we are sending 2 bits per transmission. However, in the case of MSK, only there are 2 possibilities out of the 4, and that's because we want to control the phase shift and keep the phase continuity. So if you look at the possibilities, you are sending either plus or minus based on the input signal. Sorry. Now, if you look at the diagram here, if you are in a given phase state, then you cannot jump. You have to go into the next state. So you can have plus or minus pi over 2 for this example. So if you are in the state 0, if you are transmitting 0, there are 2 possibilities. Either the current phase is 0, so you can go down by minus pi over 2, or the current phase is pi, so you can go down by minus pi over 2, and it becomes pi over 2. So at every instant, you can only move to the next possible phase. Okay, if you have 0, you go minus. If you have 1, you go plus. But you cannot transmit this, so you have to go into steps. If you are here, there are 2 stages, and so on and so forth. There are in total 4 possibilities, but we can only move to 1 out of 2 at a time. If you want to read more about this diagram and the details, I advise you to read Heiken, Communication Systems. Our focus now is just to recall the modulation techniques, and we are going to focus on the performance. Now let's address the power efficiency, the power spectral efficiency, and the bandwidth of M-ary FSK. If all the M symbols of the FSK signals are separated by 1 over 2t, of course we need to separate the frequencies to make sure that we can distinguish them, and this is the requirement to maintain orthogonality. Then the baseband power spectral density of the MFSK is shown in the following diagram. Of course, as we increase M, the bandwidth requirement will increase. So that's for M equal to 2, 4, and M equal to 8. That's the power spectral density. Now, if you want to look at the bandwidth efficiency, then let's look at the bandwidth required. The minimum variation is 1 over 2t. We can assume approximately that we'll have multiple of that by M, where M is the number of symbols. Of course, T here is the symbol duration, and you know that T and TB are related. In case of binary, then capital M equal to 2 and T equal to TTB. This is the symbol time, this is the bit time. So we expect that the symbol time will take more than the bit time depending on the value of M. The bit rate is 1 over the bit duration. So we know the bandwidth, we know the bit rate. To find the bandwidth efficiency, or the bandwidth efficiency is basically measured in bits per second per hertz. That's rho equal to RB divided by B. Now let's do the substitution here. So if you just do the direct substitution for the bandwidth and also for the rate, we will get T. Of course, we'll replace this with TB so that TB cancels out, and we get the following expression: 2 times log base 2 of M divided by M. So we find out that for FSK, the power spectral efficiency or the bandwidth efficiency is related to RB over B, and it's just a function of M. So we make a small table here where M is 2, 4, 8, 16, 32, and we just substitute in the equation. We found that the power efficiency for the case of 2 and 4, it's the same, it's 1 bits per second per hertz. And if you start going up, then the utilization of the spectrum decays down. The power spectral efficiency is less because FSK is bandwidth inefficient. For the noncoherent orthogonal modulation, We say that we have non-coherent, which means we are not getting the time information. Consider two orthogonal signals. Consider two orthogonal signals, S1 and S2. I'm just coloring here to make things simple. Which every one of them is covering equal energy and for the time duration from 0 to t. The two non-coherent orthogonal are sent over an imperfect channel. We have to assume that the channel is imperfect, otherwise we always have coherence. So there will be some shifting in the carrier phase, and that's why we have a change of color here. We sent S1, but we will receive G1. We sent S2, but we'll receive G2. So G1 and G2 are the phase shifted signals. They're orthogonals, and they have the same energy, but they are not coherent. They are having some phase shift. So the received signal will be the shifted signal, G1 if S1 was sent, and G2 if S2 was sent. And of course, we'll have added noise to that. So the noise is additive. We'll assume it to be additive wide Gaussian noise, AWGN, with zero mean and power spectral density of N0/2. This is what you see in this slide is the non-coherent orthogonal modulation generalized binary receiver. Because we don't have a coherent detector, we will not be able to multiply by the carrier. So we have filtered matched to the signal S1, another filter matched to S2. We do envelope detector. We need the envelope because we just use the amplitude because we don't have phase information. We will be sampling at the end of the duration and compare the two branches. That's in the case of binary. If we have M-ary, we'll have multiple branches. So the carrier phase is unknown. The receiver relies on the amplitude, and hence we are using the envelope detector. Error occurs if larger amplitude caused by noise alone results in the wrong decision. If for any reason the amplitude in one of the branches, which is not supposed to be the true one, become greater than the other one. So what the comparison device would do, would compare the upper branch with the lower branch and make a decision on S1 or S2. Now, specifically for non-coherent binary FSK, what we have seen in the previous slide is the generic form for the non-coherent orthogonal modulation, and now we'll just focus on binary FSK. We know that the performance we have seen to be 1/2 exponential minus EB over 2 N naught. In the binary FSK, if in the binary FSK case, the transmitted signal will basically have two different frequencies, and those frequencies, to maintain orthogonality, should follow a certain constraint. Okay, so again, non-coherent binary frequency shift keying is a special case of non-coherent orthogonal modulation. Orthogonal is generic. We're just focusing on the frequency case, and the average error probability is given by the following expression. So the non-coherent receiver, which we had before, but now we can just focus more on the example of binary FSK. Again, we'll have matched filter, but this filter is now matched to the two different frequencies. We have F1 here and we have F2 here. The envelope detector is used because we have no coherence, and then we take a decision at the end of the sampling time. We compare the two branches and we conclude. So this diagram is pretty much the same like the block we had in the previous slide, but now we focus more on the specific example of binary frequency shift keying. Differential phase shift keying. One of also the important modulation techniques that are used in wireless applications includes the differential phase shift keying. It's an example of non-coherent orthogonal modulation. And in the DPSK the transmitter consists of two stages. I think we have this before. I will maybe share the video with you, and if you can go to Introduction to Communication Engineering or Communication Engineering 1 course. And then we discussed the DPSK in general. Here we'll just quickly review it. It consists from a differential encoding of binary waveform, and then do the phase shift keying. So it's like PSK, but we start by differential encoding. So the transmitted signal of the binary 1, symbol 1, okay, will be, it depends, of course, we'll have some sort of memory here. So we have two durations. If we are transmitting this from 0 to TB, and the next duration from TB to 2 TB will just be consistent, will not change the waveform, will have exactly the same waveform. However, in the case of 0, we're going to flip the waveform. So in the case of transmitting a 0, then you can see that we have a phase shift of pi or a minus sign here. So if from 0 to TB we're sending a waveform, then in the second duration we'll be sending the inverse of that waveform. For differential phase shift keying, the performance is different. If you compare it with FSK, you'll find that we're not dividing by 2 here, and we'll come to that. So the special case of non-coherent modulation, okay, with the given details. So the time duration to find the bit will span the time duration will span 2 bits. Okay, so differential phase shift keying, the steps is first generation and decoding or detection of DPSK. If binary symbol is transmitted, we'll leave the data unchanged. If binary symbol is 0, we're going to introduce change. That's differential recoding. So differentially encoded sequence introduces a phase shift in a carrier with angle 0, and this is why we call it phase shift keying. So the example says here, find the differentially encoded data for binary sequence. So this is a sequence, all right, and this is the differentially encoded sequence. So forget about the red here, just focus on the green. So we'll have 1 here. Okay, if you have 1, we'll keep the transmission the same. So 1. This is 1 now. 0, it means do a change. So this becomes 0. 0, I'm going to make a change, 1. If we get 1, we keep things as is. So 1, 1. 0, okay, change. 0, change. 1, keep as is. 1, keep as is. So this is a differentially encoded. So this line is basically just a delayed version. So every one of these here will show up as in the next bit here. So these are just a pure shift. This is needed to find if we want to compare and find the difference. So now you can see here that the data is in the change. So when we transmit now for 1, we're getting zeros. We're now doing phase shift keying for the coded sequence, for the green. So 1 will send 0, and 0 will mean that there is a shift here. So 0 will shift by the carrier by a pi. Okay, so basically from here to here we have BFSK. But before doing BFSK, we did the pre-coding, and that make it differential phase shift keying. Or from here to here, we have normal PSK.